Very good morning to everyone. We are back into our lecture series on advanced hydraulics. We are for last few classes going through the module 2 on uniform flows. In the last class we discussed on the channels having compound sections, how the compound section was defined, how to evaluate mean flow velocity for compound sections, that was also discussed in the last class. We also suggested on how to evaluate normal slope. Suppose if discharge and normal depth, if it is given for a channel, how to evaluate the normal slope of the channel, that was also discussed. Today we will see on how to compute flood discharge using uniform flow approximation. To compute flood discharge using uniform flow approximation. So, let us just go back before going into the concept what is meant by flood discharge and all, and you have to use the uniform flow approximation and all. Let us recall in the uniform flow computations and all, what are the various variables or what are the various things you have gone through. If you want to use Manning's uniform flow approximation and all, what are the various quantities in those equations? I will just briefly enumerate them. You have already seen normal discharge, we gave it as symbolically Q. You have seen the uniform flow velocity, we gave it as V bar. You have seen the concept called normal depth, Yn. Manning's coefficient of roughness, in the Manning's equation you have also seen the channel slope or bed slope or energy slope coming into picture, S naught or SF coming into the picture. The geometric shape of the channel, that give rise to cross sectional area A, hydraulic radius R, etc. So, if these parameters, if these 6 quantities are related in Manning's equation for uniform flow computation. So, for example, if you are given the all other parameters, say normal depth Yn, coefficient of roughness N, channel slope S naught and the geometric shape of the channel A and R, if they are provided to you, you can easily compute the normal uniform flow velocity as well as the normal discharge Q in the channel. Similarly, if normal discharge Q, if it is given to you, you can, and if the other parameters normal depth, coefficient of roughness and geometry of the channel, if they are also provided, you can easily compute the normal slope of the channel. So, these some of the problems related to them also we have computed and all. So, you have to recall them, you have to use those concepts. Now, to evaluate flood discharge or to compute flood discharge, compute flood discharge in a channel. What do you mean by that? What do you mean by flood discharge in a channel? You have to take a considerable reach of the channel. Earlier we were dealing only with one cross sectional area of the channel. Now you may need to take the considerable reach of the channel, and along the reach of the channel wherever it is flooded or wherever it is overflowed, all those quantities, how you can measure the corresponding discharge and all, you need to take into account. Going back into the uniform flow computations, you have seen that generally for uniform flow, your bed slope, your slope of the water surface and the energy slope, all of them are equal. This approximation is quite valid for general shape channels or even for laboratory experiment channels and all. However, if you go through the natural streams, rivers and all, you may seldom see where all these parameters are equal, means exactly equal. To approximate uniform flow in those natural streams or rivers and all, you need to approximate, you have to suggest that your bed slope is approximately equal to your energy slope or like that, or it is approximately equal to the water surface slope and all. Like that you need to give certain approximation, then only the uniform flow approximations can be employed for natural flow. So, as you have seen in compound sections channels and all, most of the natural streams may be having compound sections. So, the velocity pattern along the same cross section of the channel, it may not be uniform, it may be having different, means along the flood plains the velocity may be quite different, along the main river channel or main channel of the carrier channel or main portion or main body of the channel, it may be having different velocity. So, that we have seen in the last class, we have already gone through them. So, you have to now think on certain approximations here, as velocity may be rarely equal along compound sections, along the same cross section in a compound section and all. You may have to give some approximations, certain approximations. Definitely the computation of energy slope means if along a cross section, velocity along a cross section of compound section are rarely equal. Therefore, energy slope may not be same as bed slope. It is quite possible in natural streams. Then you need to incorporate correction factors, or we have seen certain things and all. Even if you do that, you will see the energy slope and bed slope, they are somewhat not exactly equal and all. So, you need to devise certain method. So, here comes the portion, rather than taking only one section of the channel, for computing flood discharge now you have to think in terms of the stretch or reach of the channel along which the flooding is getting occurred. Say if you have say a channel reach like this, so its cross section may be like this and it is flooding along these portions also. Let us approximate it like this. So, in such a type channel portion, along the flood plains or along the side channel portions and all, you may have to incorporate different velocity. In the main body it will be different velocity. Subsequently, along this entire reach, how much quantity, how much discharge is available from the flood plain as well as along the main body, the combined discharge and all, how to evaluate them. You are going to take the stretch or reach of the channel you have to do certain averaging along the reach and then try to evaluate the discharge. Let us go through them. So, for such a type of figure, you may see that you require now to take energy slope rather than the bed slope. You need to think in terms of energy slope first, because the energy parameters, energy head and all, it is quite different in the upstream. For example, here this is the upstream portion and this is the downstream portion. So, the energy head, the difference in energy head divided by the length of the ridge, that will give you the energy slope, the bed slope correspondingly. And if they are not equal, you have to first evaluate the energy slope. You have to think in terms of energy slope here first. So, the difference between the total heads at the, you may calculate the total head at the upstream, you may calculate the total head at the downstream. Subsequently, the difference in head divided by, so difference in total head at upstream and downstream divided by length of reach. This will give you the energy slope. I hope you know what is meant by total energy head. That is, it is consisting of pressure head, section head or datum head, what you say datum head as well as pressure head, datum head and velocity head. So, most of the uniform flow computations, you were able to avoid the energy velocity head to compute the energy head, because the velocity in most of the cases, if it is a regular section and all, they are quite equal, and the magnitude of velocity head at upstream and downstream, they would have been almost same, and it may not be creating any change in the energy slope. That is not going to cause you any change in the energy slope. However, for such compound sections or such flood discharge, flood causing channels and all, you may need to take into account the total energy at the upstream, total energy at the downstream. You have to evaluate the energy slope first, then you have to compute the corresponding discharge. So, here then you will see that during the flood, when it enters the flood plain and all, the velocity will be drastically changed along the flood plain. In the main body, it will be different. So, the flood stage and the discharge, they may be, if you want to, if you are able to correlate the stage in the flood plains, that is a flood stage and corresponding discharge. So, if you are able to correlate flood stage and corresponding discharge, and if they are having some gradual changes or gradual changes and all, if they are there, that is, if the flood stage, if it is changing gradually, then the discharge is also discharge along the flood plains, that is also changing gradually, or like that. If you are able to correlate them, then you will be able to give uniform flow approximations for the flood discharge also. Otherwise, for natural streams, wherever flood is occurring, these components are there, it is quite difficult to give uniform flow approximation. So, this is quite essential. There is this portion suggesting that you have to correlate flood stage and its corresponding discharge. If you are able to do that, then that is fine. Then uniform flow approximations hold good. So, what are some of the methods which you can use? How you can see? So, mostly for such this thing, when we suggested that if there is a gradual change in flood with respect to the flood discharge with respect to the stage of the flood, and or if you are required to have historical note on flood marks in the channel. So, various historical means you have to give elaborate, you have to note the various flood marks in the channel and all. So, at during the peak rainy season and during the peak flow of the river, this was the mark of the flood at that time. During the lean period, this is the mark, or means at various situations and all, what are the different flood marks and all. You can just either capture them in photograph, or you can note it, you can do the survey related to the marks and all. You can just obtain it as a data. So, once you obtain the corresponding data, then you can use, say for example, slope area method, which we will see today, to evaluate flood discharge. Then there is another method called contracted opening method. So, here as we mentioned in the earlier portion, so in such a channel portion, in such a type of channel, this thing in the upstream and downstream, you are directly applying the energy equation. Here in the contracted opening method, in the downstream and all, principle of energy conservation and all is being directly employed, and you are trying to evaluate the corresponding discharge. So, that we are not going to see in today's lecture and all. Definitely we are going to explain to you on the slope area method. So, the thing is that we require informations on, for this slope area method, we first require informations on the energy slope. We require certain information. So, that is energy slope in the reach, you may also require, or your average cross sectional area of the reach, length of the reach, roughness coefficients, so like this some of the parameters are required. So, we will just briefly see what is the thing. Say if the channel reach is like this, the upstream portion, downstream portion, length of the reach is L, length of the reach. Then the methodology involves, you have to understand which is, first identify which is upstream portion and which is downstream portion, that you need to understand first by seeing the direction of flow and all. Based on that, you have to now first evaluate. So, the procedure for the slope area method, it involves, the first step is identify area of cross section both at upstream and downstream. So, in the first method you will be identifying the areas of cross section. Not only that, you will be identifying areas of cross section at upstream, area of cross section at downstream. You are able to, you have to evaluate the hydraulic radius at upstream, hydraulic radius at downstream. You can see if Manning's coefficient, if it is same at upstream and downstream, well, good, you can take it like that n itself, or you can suggest n at upstream and at downstream, like this you can suggest them. Now, using these parameters, what you have to do is that you have to compute conveyance factor both at upstream and downstream. The conveyance factors at upstream and downstream, you need to evaluate them. I hope you are aware how to obtain conveyance factor. This is 1 by n A r to the power of 2 by 3. So, for the upstream compound section or normal simple section, whatever be, you evaluate the corresponding conveyance factor. In the downstream of the reach, what is the conveyance factor? Both you need to take into account. Now, for the entire reach, the second step is you are now obtaining average conveyance factor for the entire reach. So, this average conveyance factor for the entire reach, it can be given as K average. This is nothing but the geometric mean of the conveyance factor at upstream and downstream respectively. This is the formula for geometric mean. So, that has been directly employed here. So, once you get the average conveyance factor, the third step involved is you have to first assume, that is, in this method first you are assuming velocity head is not having prominent role in energy head computation. Just this is a brief assumption, initial assumption, or you can as you might have seen in solution of various differential equations with respect to time and the initial conditions or like that. So, this is just an initial approximation. We are suggesting that velocity head, initially we are assuming that it is not having prominent role in the computation of energy head, or rather than that you can see that it is not having prominent role in computation of energy slope. So, that will be better terminology, not having prominent role in energy slope. This is the initial assumption. In that way you can find slope of energy SF. This is nothing but equal to del y by L. I will tell you what is meant by del y by L. So, the reach, if I just draw the front view of the thing, and if this is the channel, this thing, see, this is the upstream section, this is the downstream section. Now, whatever drop in water surface is there, we are now approximating that. You know that for uniform flow, water surface slope, bed slope or energy slope, all of them are approximately equal in general channels or in regular shaped channels and all. Right now, we have come into dealing with the natural streams where flood discharges occur. So, there is a difference in level of water surface at the upstream and downstream. That difference is given by del y. So, this del y by L, whatever is there, we can initially approximate this as energy slope. That is not theoretically correct, but that is the initial approximation. We are suggesting that the component of velocity head in this case is very negligible in determining the energy slope. So, therefore, the energy slope SF is given by del y by L. If this is the case where del y is equal to fall in water surface from upstream to downstream in the ridge. Okay. Now, based on this particular value of slope, based on this particular value of slope, you can evaluate and you can give a first approximation for the discharge in the entire channel Q. The discharge in the entire channel reach, from the entire channel reach, the discharge, it can be given as Q is equal to K average into SF to the power of half or root of SF. So, please note that we had given an approximation for the energy slope and we are substituting it. So, let me give this as a first approximation, and this is not the correct discharge actually from the actual correct flood discharge from the channel. This is just a first approximation. Now, using this value of Q, you can easily now evaluate what are the velocities at the upstream and downstream. That is quite possible, right? Uniform flow means generally the discharge is same at upstream and downstream. So, you can easily evaluate. So, the fourth step is using the first approximation of discharge. Now, evaluate velocities at upstream and downstream. Evaluate them as shown in the figure here, at the upstream and at the downstream, whatever are the velocities. How will you compute them? You know the formula for that. So, Q is equal to AV or V is equal to Q by A, directly substitute them. So, we will get at upstream location, you will get the corresponding velocity V US. At the downstream section, you will get the corresponding velocity V ds. Based on this, you can easily now compute velocity heads at upstream and downstream. Just compute them. For example, if alpha up US is energy head correction factor, that is energy correction factor for velocity at upstream section. Similarly, alpha ds energy correction factor at downstream. So, if you have these data, then you can easily evaluate. So, at upstream the section, the velocity head will be now alpha us v us squared by 2g. Similarly, at downstream section, the corresponding corresponding head will be alpha ds v ds square by 2g. So, once you have these quantities, now you require to use these two heads in the energy correction factor. So, in the energy slope, you have already determined the energy slope earlier. So, that was the first approximation. So, now you know drop in water surface, that is a measured quantity. So, that is not going to change. Okay. Therefore, energy slope for the entire reach can be given as SF. This is equal to the change in this change in energy head HF, drop in energy head, total energy head HF by the length of the channel. This HF includes now your drop in water surface plus a factor small k into alpha us v us squared by 2g minus v ds squared by 2g. Once you obtain this corresponding form of the energy drop, this is the energy drop in the entire channel reach, energy head of energy drop in the entire channel reach. This k factor, it is an empirical, it is obtained from an empirical this thing and various experimentation and all. Various scientists have suggested that k can be given as 1 if your channel reach is contracting. If your channel reach is contracting, that means V upstream is less than V downstream if your channel reach is contracting. In that case, you can give k is equal to 1. If V upstream is greater than V downstream, channel is expanding, you have to take k is equal to 0.5. This also the many scientists have experimentally obtained those things and all, or experimentally or doing some analytics and all. So, we will just incorporate them in our analysis here. So, once you get this thing quantity, now you get a, you are now getting a modified energy slope as mentioned earlier. So, SF, let me give this as 1. This is equal to S of 1 is equal to now del y plus k into alpha upstream V upstream squared by based on this. You can evaluate the modified discharge, or you can give a new value for discharge. Q is now equal to k root SF that has been modified. Fine. So, this you can give as the second approximation for discharge. Once you get this second approximation for discharge, again go back you just go back using, so using now Q2, evaluate V upstream, and that also you can give it as 2, V downstream 2, evaluate S of 2 now. So, once you get S of 2 with the same procedure as adopted, you can compute Q3, this is nothing but K times root of S of 2. So, once you get Q3, go back again, evaluate, just check it. That is, we are going back again because we are finding that Q2 and Q3, they are not same. Similarly, Q in the first approximation, Q in the second approximation obtained, they are not same. So, we are going back like this till 2 of the consecutive approximations are giving you the same discharge. So, evaluate like this till say Q in the ith approximation and Q in the I minus 1th approximation are same. So, once you get this thing, the corresponding values of SF has to be noted, the corresponding values of V in the upstream and V in the downstream, those things also have to be noted, and now you have got the discharge, flood discharge. So, this is how you compute, means this is how you compute the flood discharge using uniform flow approximations for the natural streams. So, as I mentioned earlier, you are dealing with the entire channel reach. So, if you are having many such reaches, if there are many such reaches of different lengths, say this is L1, this is L2, L3, L4, L5, etc. n, like this you have many reaches. Then for the entire natural stream, you can now average the discharges. So, using the slope area discharge method, you have evaluated the corresponding Q from this reach. Similarly, you can give it as Q1. What is the slope, using slope area method, what is the average discharge from this thing Q2? It is not average, it is the slope area method by approximation, means by iterating you have arrived at Q2 as the discharge from this reach, Q3 as the discharge from this reach. Like that several reaches are there. You can average the discharges for the entire length of stream that is having different reaches. Like this you can summate for the entire this thing, and you can just average it and get the average discharge for the entire natural stream. That is the way you can compute. You can use appropriate weights also to compute the discharge. Next, we will just go through what is meant by uniform surface flow. You have heard about uniform surface flow, or especially during the rainy season and all, you may see various means on the overland, flow of water occurs from the overland in a form of thin sheet, means the depth of flow will be considerably small, but still there is some flow of water in a sheet form through the surface, whether it be the whether it is be like this along the sheet, it may be going like this and all, various type of flow you might have observed in the nature. You can even give approximations for overland flow through uniform flow computations. That is also quite possible. Say if this is your land surface. So, before the water reaches, when the rainfall occurs, after some quantity getting infiltrated, and before it reaches the main channel or before it reaches any channel, it flows along the ground in a form of thin sheet. So, this depth, it is quite small. So, let me say this depth as y m, some very small depth y m, and it may not go beyond this depth also, mostly it is a very thin this thing. So, in this case, if you observe that, again your basic fluid mechanics principles and all are coming into picture. The depth of flow is small, of course. So, it may be having some velocity distribution of this form with respect to depth. You will observe that for such type of flow, friction or the resistance due to viscosity and all is prominent in such type of flow. So, viscosity is important in overland flow. So, if viscosity is important, how will you compute the uniform flow now? So, you have to use the Newton's law of viscosity. I hope you know what is Newton's law of viscosity, which suggests that the shear stress along the bed of the channel or shear stress along the bed of the pipe is nothing but proportional to the gradient of velocity, and the proportionality constant is called the dynamic coefficient of viscosity, mu. Okay. So, the same thing you need to apply here. So, therefore, let me just give the overland flow in a magnified form. Here this is your depth y m. So, it is having a velocity distribution. So, in such cases, just take a small elementary strip from the top surface, of water. You just take the small elementary strip, and this strip is at a height y from the bottom of the ground. Now, in this strip, whatever is there, you will see that what happens is that for such type of overland flow, viscosity is prominent, we suggested that. So, there will be a considerable amount of friction that causes, that frictional force will be acting in the opposite direction, and that causes or that opposes the motion of flow in the downstream direction. So, how the viscous flow affects these things? If you take this elementary strip, it has its weight acting downwards. So, the component in the flow direction, whatever is there, now that is now being compensated, or you can suggest that is being now dealt with the frictional force along the bed. So, you have to equate it now. So, what is the frictional force along this direction now? What is the frictional force? You will see that the frictional force, we are, please note that we are taking laminar flow approximation. So, the frictional force per unit area along the perpendicular direction of the screen here given to you, per unit area, whatever frictional force if it is there, let us consider that as your shear stress. You know that force per area gives you the stress component in many of the situations. So, or the stress is having the units of force per area. So, let us give that as shear stress. This is nothing but rho g into, say, what is the thing here? The depth here is ym minus y, and you know that rho g is the weight of the liquid in this thing, in this within this particular depth. So, the rho g ym minus y into the slope, means you need to take into account the slope here. So, we are equating the component of the gravity force in this direction with respect to the friction force. That is what we are doing it here. That can be given it like this. So, this is nothing but, if you again go through the same equation, rho g ym minus y s naught, this is equal to, you use the Newton's law of viscosity, you are equating it to this, with respect to Newton's law of viscosity. From this equation, just rearrange the terms. So, dV by dy is nothing but equal to rho g s naught by mu ym minus y, or you can use this relationship now to obtain the integral, say v, the velocity in that portion of the small portion of that overland flow and all. It is nothing but integral rho g s naught by mu ym minus y into dy. You will see that all these quantities are constant, rho g s naught by and mu are constant with respect to y. You are going to get this equation as v is equal to rho g s naught by mu y into ym minus y squared by 2. Okay. So, you are getting a quadratic expression for the velocity in the overland flow. You can now compute the average flow. This is with respect to any height y. So, you can compute average velocity at any section for overland flow. You can give this as v bar. This is 1 by ym is the depth of the overland flow, v dy. You just substitute the quantity of v whichever we have given it here, you will get this as rho g s naught by 3 times mu into ym square. So, we are these portions and all, we have referred the text from Ventichow on open channel hydraulics. So, this average overland flow velocity is computed in this way. So, this is as good as your uniform flow, means this velocity is same as the uniform flow. You can also suggest that the discharge per unit width, discharge, this is velocity. So, discharge per unit width in the uniform for the overland flow, you can give this as equal to q, and this is given as some coefficient CL into ym cube, isn't it? What we have done? We are just CL into ym cube, because here this is velocity, and velocity into the width means whichever means discharge, you are talking about discharge per unit width. So, you have to take the sections appropriately rather than unit area, you are taking unit width. So, CL into ym cube, it will be a third degree equation with respect to your depth of overland flow. So, your CL is nothing but the coefficient, same coefficient rho g s naught by 3 mu, it may be observed like that also. you may see such phenomenon and all. Like this way you can compute uniform flow for overland flow cases also. So, today we will like to stop it here. As a portion of interest or curiosity, I can just ask you one question. You have seen in road sections, you have seen in various roads and all. So, the road is having a gradual slope, and at the two end portions of the road, say this is your road, and at the two end portions you may see small gutters on the road, right, at this portion and at this portion, like this you may see gutters in the road. Now, you can use your uniform flow approximations to compute flow along these gutters, that is also quite possible. You can also use your overland flow approximations along these portions to find the discharge or discharge per unit width along this thing, and then arrive at the discharge quantity here, then subsequently incorporate uniform flow along this main triangular gutter channel and all. If I just elaborate it, if I just show it in a elaborated way, it may look like this, something like this, then like this. So, this is your triangular main channel, water may be there, but okay. A question as a part, as today's quiz, in today's quiz we are just asking you one question only. For the same triangular gutter section, for the triangular gutter section, this depth is given as y and the slope is given as 1:b. If this is provided to you, how will you evaluate, or how will you evaluate discharge Q in the triangular section? So, you use uniform flow approximations. So, you should be aware with the geometry of the triangular section, then you try to compute it.